first of all, this is what I'm going to be talking about is a new stuff which is joint work with Marco Carmazina, Valentin Cabanez, and Igor Oliveira, and I think all of them are here. Thank you so much for coming. So if I say something weird, you can correct me. And this is this project has kind of complexity side and bounded arithmetic proof theory side. So I'm going to focus pretty much exclusively on the logic side, the bounded arithmetic side. The whole idea of this project was the interplay between the two. So just to say, if you have a question, please ask by voice, or you could post it in the chat. I have a chat window up, so unless I'm deep in my thought, I should be able to see it. Okay. So let me tell you what it is about. So in complexity theory, the big quest is to understand the relationship between different types of complexity classes, resources, like does non-determinism give you something more? Does randomness give you something more in terms of kind of problems that you could solve and how fast? So complexity quest in a way is answering questions along the lines of P versus P and friends. But you could also think of a meta-complexity quest where rather than saying, let's just solve a complexity question, you ask, what is the complexity of reasoning to resolve those questions? And I would imagine that this should be near and dear to all the constructive mathematics people in the audience, which has a lot of fantastic constructive mathematics people. So here, basically, the question that we are trying to study is, what is the complexity of reasoning? And I'll define it a bit more precisely. That's needed to resolve questions about complexity. Questions that we don't know how to solve, questions for which we have various barriers, but questions about complexity. So in a way, this is more of a proof theory quest, is understanding how much we could say using efficient reasoning, big theories of arithmetic. I will talk at length about it later, but what is the power of efficient reasoning for solving meta questions? What is the power of polynomial time reasoning for talking about the power of polynomial time, or of P versus P? So far, nothing here is new, in a sense that the power of efficient reasoning had been studied since a long time ago, in particular by people in the audience. What we are going to talk about today, though, is one interesting connection. And this is a connection that was inspired by bounded arithmetic to complexity of learning how to solve problems, particularly hard problems. So rather than asking, how do we solve, for example, Boolean satisfiability, we could ask, what would it take to learn to solve Boolean satisfiability? And interestingly enough, there is a very nice interconnection between complexity of learning to solve hard problems and the power of efficient reasoning. The power of reasoning tells you exactly what kind of learning you could do. And for the other direction, if we understand the complexity of learning paradigms well enough, it can tell you something about probability and bounded arithmetic in particular. So this is pretty much the outline of the whole talk. It's about the interrelation between probability in particular bounded arithmetic, and complexity of, and I'll define it, learning how to solve problems such as satisfiability. So by the way, there are things that I'm going to define at length. If it's too much, please tell me to move on. There are things that I will kind of mention in passing. You're welcome to ask what they are, or you're welcome to say, okay, that's kind of not relevant. I get the gist of it. I don't need to know the exact definition. But again, please ask me if you have questions. So I mentioned that it's P versus NP and friends that we are talking about. So let me talk about the friends of P versus NP. This seems very counterintuitive. We don't know how to prove that P is not equivalent P. So let's solve a harder problem. And here's what it is. Rather than talking about, is there an algorithm to solve satisfiability for all the possible instances on all the possible sizes of the input, let's talk about a more powerful computation. Now, for every input length, you are allowed to create a Boolean circuit. Basically, Boolean circuit, we just think about something which operates with AND or not, takes as an input N bits, and outputs, well, sometimes 1 bit. It can output something much bigger. It can have multiple outputs, but it's a concrete object for every size N, and for every input size, it's supposed to solve the problem. You don't care what happens for other input sizes. So what's kind of useful about circuits is that we are not really talking about a single algorithm that has to work for infinitely many inputs. Now, say, let's fix an input length. Is there a circuit that will solve the problem? And indeed there is. The question is what size it has. We could always brute force and say, if the input looks like this, output this. If the input looks like that, output that. It will take us roughly exponential time or exponential number of gates in the circuit. So if you want to talk about efficient computation, we want the number of gates to be small, that's polynomial. And by the way, a Turing machine can easily be converted into a sequence of circuits. Basically, there is a very kind of streamlined construction that you take a Turing machine and you build a circuit from it. For a given N, from description of Turing machine, it's easy to build a circuit. So what do we know about circuits? Well, we know by the counting argument, going back to Shannon, that vast majority of Boolean functions require exponential size circuits. The argument is very simple. It just says there is a ton of Boolean function. There aren't that many circuits of small size. But here's where it gets interesting. We don't know of any hard function in kind of a reasonable complexity class. So for a problem in NP, satisfiability, the best lower bound we know is that satisfiability requires circuits with slightly more than 3 gates. By the way, it's a very active area of research. The slightly more gets improved by a decimal point every once in a while, and every time it's big news. So this is a kind of a disconnect. On one hand, nearly everything is hard. Nearly everything requires exponential size circuits. On the other hand, actually pointing to a problem that requires a circuit, as in describing it with some reasonable complexity class, we have no idea. Well, we have no idea the recurrent Riemann complexity theory. So, yeah. So what is the hard problem that we are trying to solve? So now, rather than saying, can we solve everything in NP, in particular Boolean satisfiability for Boolean propositional formulas by some algorithm, we ask, is it possible to solve it by a family of circuits where every circuit for every n can come from who knows where, and maybe are no resemblance to circuits for other n. And so if we could show that no, there is a problem in NP that doesn't have such a family of circuits, then definitely P not equal NP. But it is still possible that this very, very powerful non-uniform setting can let us solve problems in NP, and yet P is not equal to NP. So just to say one more thing about the circuit setting, it's pretty easy to solve undecidable problem using this setting. For example, say you have a problem which says your input is a Turing machine's number encoded in unary, and you want to say whether this machine holds on blank. Very easy. For every input length and for every Turing machine, because it's in unary, you have just one input length. You produce a circuit, or don't produce it. It magically appears of constant size because there is only one answer. It either holds on blank or it doesn't. So this is how powerful even constant depth or constant size circuits are. So in particular, we know that it's not NP equal to P poly, but NP in P poly, because we cannot solve undecidable problems in NP. But still, it's not really clear, and actually probably believed to be not true, that satisfiability can be solved by even polynomial-size circuits. Okay. So you may ask, okay, NP, we know the kind of thing is hard. So what about problems in polynomial time? In particular, is it possible, well, all the problems in polynomial time can be solved by polynomial-size circuits because we can convert Turing machine to circuits. But is there a specific power such that beyond this power, all of the polynomial time can be solved, for example, by quadratic circuits? We don't know. This is actually not, I don't know what the intuition is about it being true or false, but for example, think of a click problem. To describe a click, you kind of, how should I say it? So we know that for click, we need large monotone circuits. So even for some click problem is an NP, but you could think of something that describing a click as something that may not necessarily be doable in a small space. But anyway, so here are some of the questions. We are making our problem harder, and we are asking what kind of power of reasoning do we need to prove those statements if they are true. Of course, they may be false, but if they're true, what does it take to prove them? So just to say what kind of statements we are talking about. So we want to talk about a language L, for example, satisfiability computable by a family of circuits of size n to the k, or some constant size n to the k. So here's a formula that encode the statement: for every input length, there is a circuit, again, magical circuit, no assumptions, that on every input of the correct length outputs exactly the value corresponding to the language. Okay, so we have input lengths. For every input length, there exists a circuit such that for every input string, the circuit does the correct thing. Well, we could also say for every language in polytime, but let's just stick with this. This is not a very complicated formula. This is a formula of the form for all exists for all, and then something fairly simple that says, yeah, you could figure out the something in the circuit and evaluate it and get a value. Okay, and this is the kind of statement that we would like to study, the probability. So just to say that the idea of studying lower bounds in particular and upper bounds goes way back. I think the main focus, at least in Razborov's work and some of the later work, was on proving lower bounds. And here we will be mostly talking about proving upper bound statements. So the main message of this talk is something that you are intimately familiar with. A proof of an existence of an object often provides more information about that object than just its existence. In particular, a constructive proof of existence of an object gives you an algorithm. And what we are studying here is what kind of proofs give you what kind of algorithms. Okay, this is the main thing in the talk. And after that, I'll start getting into details. So just to tell you a little bit what I mean by constructive proof, let me remind you of the Herbrand theorem, or at least some version of Herbrand theorem, which says that if you have a universal theory and you could prove some statement of the form for all x exists y and a quantifier-free formula, then there are constantly many terms in the language of that theory such that at least one of those terms correctly computes this y for every x. So this already kind of tells you where the constructive part is coming from. If an object exists, there are constantly many terms in a language that can tell you what it is. And you could go over all of them and figure out which works for every x. So this is the main idea. This is where that intuition about the probability giving you algorithm is coming from. So I will briefly mention our setting. If you have more questions, I could dwell a little bit more on it, but just for the sake of time. So what do we mean by efficient reasoning or feasible reasoning? We will be working with bounded arithmetic, with big series of arithmetic where all quantifiers are bounded. And when we are talking about the power of reasoning for a theory, usually we mean what kind of functions it can prove total, what kind of statements it can prove. And the big part of it is what you can define in the theory. And for the constructive part, the beautiful part, the witnessing theorem. If you could prove something, what kind of algorithm does it give you? In particular, if you've seen theories of bounded arithmetic before, we will be looking at variant of PV for polynomial time reasoning. That's the theory that just operates with everything which the polynomial time computable function. We will be looking at analogs of Sam Bass's famous SI2 and TI2 bounded arithmetic hierarchy. And some of our results, when we are talking about randomized computation, would use Emil Yerzhabek's, well, he didn't call it that, APC1, APC2, or at least the related series. And for convenience, we use two-sorted framework of Cook and Nguyen. Well, it goes back to Tambella, but we follow the book by Steve Cook and von Nguyen. And the reason we are doing it is because it allows us to talk about all the classes starting from way down, a kind of constant depth circuits, first order definable, all the way up to polynomial time hierarchy. It doesn't get us out of polynomial time hierarchy, but gives us a streamlined way of build series for all sorts of complexity classes. So the standard definition for those theorem series is you have standard axioms for numbers and strings. The only things here you could do with strings are look at its lengths and check if the index I is 0, 1. And kind of the main axiom that differentiates between power of different series is for which formulas can you get a characteristic string. Once you get a characteristic string, you could do an induction on it. So if you operate with polynomial time predicates or have polytime function symbols in your language, so in terms of polynomial time, then for every polynomial times predicate, you could get a characteristic string. And that's the polynomial time reason. And the series, the main series that we will be using are the very basic theory that only captures things computable by bounded depth circuits, which cannot even do parity. We also look at the theory V1, which corresponds to buses S1, 2. And for sigma 1 definable formulas of an existential quantifier, it captures polynomial time. To capture polynomial time a little bit more tightly, well, it's not known, but believed to be a little bit more tightly, we will be talking about the series where we just throw in all the polynomial time functions or whichever functions we want, and get a theory where basically all the terms are of exactly the complexity that we want. And to talk about randomized computation, we use Emil Yerzhabek's approach with adding dual weak pigeonhole principle for polynomial time functions. And here is a hierarchy. As far as I know, APC1 sits between PV because it extends PV, and in T1, 2, so kind of the P to the sigma 2. So any questions so far? Questions, comments? Okay, I am running out of time, so let me speed up a little. Just to say that on one hand, those theories are very powerful. A lot of complexity theory you can already formalize in polynomial time reasoning in PV1. It doesn't prove some of the things, and actually this was the starting point for this work. For example, it doesn't prove that everything in polynomial time has circuits of size specific polynomial. And that goes to previous work by mainly Igor Oliveira, with Krajicek and with other people. Probably the thing that kind of started that trend goes back to Cook and Krajicek 2007 paper, which studied the consequences of provability of statements like NP has polynomial size circuits in this theory. And things that we don't know how to formalize in PV, a lot of them are formalizable in APC1. Captures probabilistic polynomial time. You could prove all sorts of things. You could have existence of hard function. You could have pseudorandom generators, de-randomization. Basically, much of the complexity theory, as we know, it can be done with this kind of reasoning. So, what can those things prove and not prove? So, first of all, the main tool that we use is witnessing theorems. And probably the most well-known classic witnessing theorem is Bass witnessing theorem. Here it's stated for V1, but there are analogs for pretty much everything. So if you have a formula of the form for all exist, and then your formula, which can be, for example, with one quantifier over strings, then if you could prove this statement in the theory such that V1, then you get a polynomial time algorithm computing that witness. So if you can prove that for all x there exists y, and then the formula like that, then you can actually compute y in polynomial time. And this is already really interesting in the sense that if you can prove, for example, that primality testing algorithm works in V1, then you can get a polynomial time algorithm for factoring. And a lot of cryptography goes out of the window. But remember, when we were talking about the upper bound, it had a statement which looked a bit different. It had an extra universal quantifier. So if you have a formula of the form for all exists probable in V1, we could find the witness in polynomial time. What if we have a formula of the form for all exists for all? Well, for that, we have a KPT witnessing theorem that builds on Herbrand theorem to say that you could compute your bit, if you could prove the formula of the form for all x exists y for all z, and then a simple formula, then there will be functions or terms in language such that either the first function gives you the right answer. If not, well, it failed because there was some value of z for each, it didn't work. So there is another function that takes this counterexample to the first one, and knowing that counterexample tries to compute y again. And you continue this process every time your function takes the previous counterexample and tries to take them into account. So if we now go back to complexity world, what kind of algorithm do we get? Well, Krajicek, Pudlak, and Zgala already in 91 already talked about this in more algorithmic terms. They called it student-teacher game or counterexample computation. And the way it worked is you have your polynomial time algorithm student, which says, okay, so the answer for y is f of f1 of x. And the student and the teacher says, well, it's not quite right because here, if I give you z1, for z1, your formula phi of x f1 of x and z1 is not true. The student thinks about the counterexample and says, okay, how about this value? And then it keeps going. And what KPT witnessing theorem tells us that if the for all exists for all phi was provable, then after constantly many steps, this process will stop. Okay. Questions? If you think of what this algorithm reminds you of in computational learning theory. You may think of, isn't it like learning with equivalence queries that were studied back in the 80s? Well, it's not quite the same. We don't have samples. We don't have, in this case, we don't necessarily have randomness, but it does have the same flavor. You come up with something, and then somebody tells you, yes, it works. Or so eventually the teacher says yes. Either it works or it gives you a counterexample where it breaks. Okay, going back to our meta problems, now that we figured out what kind of algorithm we could get from bounded, we could learn from bounded arithmetic. So when I define non-uniformity, I said the circuits can be absolutely anything. They can come up from wherever, they can be completely different. That's why you could solve undecidable problem. But there is an actual range of possibilities between having an algorithm for something and having completely non-uniform family of circuits. And this is when you have an algorithm that can produce you a circuit that gets n and in time polynomial in n produces you a circuit that solves a problem on input of size n. So for example, if it's a polynomial time algorithm, then you get p-uniform family of circuits. And depending on how much uniformity you have, you're either closer to being just an algorithm, or you're closer to being completely non-uniform. By the way, just to mention, I think it comes up later on, FZPP is when a lot of time when we talk about randomness, in particular probability computation and bounded arithmetic, the convenient framework is to talk about zero error polytime computation. You have an algorithm that uses randomness, runs in polynomial times, and either gives you an answer or says, I can figure it out. And you have a guarantee that I can figure it out. Doesn't happen very often. And the FZPP just says that it actually produces some output. It computes, for example, in this case, a circuit. And this just means that it can ask queries to NP queries. So one important result about uniformity, and again, this is kind of a starting point of this and some of the previous work that I mentioned, is Santana and Williams' beautiful paper from 2014, where they said that we have no idea if all of P is in size n squared, but we do know that that size n squared cannot be constructible in polynomial time. And moreover, for every possible k, you cannot get circuit. There is a language in polynomial time for which you cannot construct in polynomial time a family of circuits of that size. So now I can finally say a little bit more precisely what we did here, at least part of it, is inspired by KPT witnessing theorem. We are looking at uniformity, which we called learn with equivalence query, LEARNEQ-uniformity. And we say, what if the process that produces that family of circuits is exactly when you have a polynomial time student who interacts with a teacher. So a student produces a circuit and asks the teacher, is it okay? The teacher may say yes, or the teacher may say no, because the circuit doesn't work on such and such input. Then the student tries again and again and again. And if the problem and eventually after R, some kind of number of equivalence queries, the student is guaranteed to get a correct circuit. And by the way, the teacher can give you good counterexample, or the teacher may give you not so great counterexamples. No matter what kind of counterexample the teacher gives you, the student has to ask at most R questions before teacher's patience runs out, and at the end of this process come up with a correct circuit. So what we did with this notion of uniformity first was to extend Santana-Williams that for every case there is a language which is not in P-uniform size n to the k, to change P-uniform to LEARNEQ-uniform. And here in different cases, we handle different number of possible queries. In particular for polynomial time circuits for problem in P, there is a problem in P such that it's not possible to learn polynomial size circuits for it, even if they exist, using only constantly many queries. And then we have other results for NP, where we have a sublinear number of queries, and there's a little bit more work and an extra assumption, we could get to polynomial number of queries results. And once we are at it, we could have we have some lower bounds for other notions of uniformity, kind of following the same template. So, but this was complexity. You're wondering now where I'm going. I'm veering off further and further from feasible reasoning and bounded arithmetic, and I only have a few minutes left. So what does it have to do with logic? The cool thing is that because LEARNEQ-uniformity was inspired by KPT witnessing theorem, if you have lower bounds for LEARNEQ-uniformity, they translate exactly back into unprovability of for all exists for all statements in the corresponding theorem. So again, so here's the kind of upper bound statement that we are proving. By KPT witnessing theorem, we get a learning algorithm with constantly many queries. Okay, so here, not quite learn, which is a polynomial time, unless it's a VPV, but whatever power you have on the theory T. And if we have a lower bound for this particular class, then we know that the theory cannot prove the upper bound. So, for example, going back to PV, suppose that PV proves a circuit upper bound, that everything is in polynomial time is computable by circuits of size n cube. By witnessing theorem, we know that it cannot just say circuits come out from nowhere. Those circuits have to be LEARNEQ-uniform constructible. But wait a minute, we now got LEARNEQ-uniform lower bounds. So even if this statement is true for arbitrary, kind of very non-constructive family of circuits, it's not provable in PV. Okay, any questions, any comments so far? Do I have 2 minutes or more?
So you have 3 or 5 minutes, whatever you want.
Okay. So let me just, thank you. So let me just say what kind of results we get. We do get the result that PV doesn't prove that P is in size n to the k. We get a similar result for V1, S1, 2. And we could go one level up to the next level of polytime hierarchy, put NP as SAT Oracle everywhere, and it still works. Actually, those results were already done by Igor and others before, but their proof was a lot more complicated. They actually had to formalize Santana and Williams in the series. Our proofs are pretty easy. I told you everything you need to know, at least for the first one. For the universal series, it just goes through directly out of KPT and out of LEARNEQ-uniformity lower bounds. Because we're working in those two sorted series of arithmetic, we are not restricted to talking about things above polynomial time. We do need to talk about some kind of computational object that we can actually evaluate, but in particular, in the theory for logarithmic space, we could talk about branching programs and can prove essentially the same statement with branching programs instead of circuits, and theory for log space instead of theory for polynomial time. And take your other favorite model of computation and a favorite theory, and chances are you could just use the same machinery to get it. And then we have some of the results which I don't think were there before in previous work for probability in VAPC1. So remember, VAPC1 can pretty much do all of complexity theory. And yet there are things that it cannot prove. Well, maybe it cannot prove them because they are false. I think we know that this part, if you talk about ZPP to the NP, that might be false, at least without the infinitely open. But at least here is something that still potentially can be true, and yet it cannot be proved in a very powerful VAPC1 theory. So let me just state the very last theorem, which kind of which shows how the interplay between upper bounds and lower bounds and different kind of witnessing can give you unprovability. So here is a statement. Even though it's unlikely, it's possible that P not equivalent P, and yet that non-uniformity is so powerful that all of NP can be done by polynomial-size circuit. Well, that would be pretty hard to prove, in particular because if the reasoning in our brain is anything like reasoning in PV or in APC1, which pretty much can do most of what we could prove, then we cannot do it, because those theories do not prove simultaneously that P is not equivalent P, or NP is not in VPP, and that NP is easy in non-uniform setting. And the proof idea is we have a witnessing for the upper bound, PPT witnessing. We have a witnessing for the lower bound statement. So upper bound statement, lower bounds, lower bound statement. And using the interplay of both of those witnessing, we can actually get the unprovability result. If you assume that P is equal NP, that gives us an algorithm that allows us to get rid of equivalence queries and get a contradiction. Okay, so just to mention some open problems, we know how to show that V1 S1 2 doesn't prove that NP is inside N to the K. But V1 is conservative over PV. It would be nice to get it down that it actually doesn't prove that P is inside N to the K. We don't know how to do it. there are a few extensions to the result that we have. For example, we're a bit off from showing that with randomized reasoning, we cannot prove that zero error polynomial time, everything there can be done in size. And to the case for that, we need some advances in complexity. And in general, those results are kind of a barrier results. But there is always a caveat that if it's true, which we sometimes don't really believe, we cannot show it in theory. Can we actually get a real independence result? So just to finish, basically, this is one example where from proof of existence of an object, you could get algorithms, and from having algorithms, you get bounds, and from having bounds, you go back and you get unprovability. So having a proof of existence of something is a very powerful thing. Doesn't need to be told to members of proof society, but a good message to spread nonetheless. Okay, thank you so much. Questions, comments?